So when people think about quantum physics, they often think about very small objects like atoms and molecules. And that is correct because the laws of such small atoms and molecules are not the same as the macroscopic laws we see in this room. But what is special about superconducting circuits is that you can make them so big. You can manufacture them as a chip, and this chip you can almost look at with your naked eye, and still they will behave in a quantum mechanical fashion. And if you are familiar with the Nobel Prize in Physics last year, it was awarded precisely to these people who discovered that quantum physics can be observed in microscopic circuits, which is what we do here in the lab.
So this lab is equipped for equipment to do research and experiments in superconducting circuits, and we do research which is both basic and applied. So over here behind me you can see 2 dilution refrigerators which are operating right now, and that is why you hear that periodic tick 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 sound. So these dilution refrigerators bring down the temperature of our devices down to about 10 millikelvin, which is about minus 273.14 degrees Celsius. And this is where we install our devices deep down over here, and then from here we have microwave cables which go all the way to the top, and then we have them come out, and then they connect with our microwave equipments which operate in the range of about 4 to 8 gigahertz, which is similar to what is used in the telecommunication sector. So a lot of these electronics have a lot of similarity to those devices. And over here, then we have all of this running the show, and we even have the computers. Then we have the cables that go from all the way top to our computers, where we actually do these experiments. We can basically from here control all our superconducting circuits and also acquire data from here. So this superconducting circuits, their fabrication is quite similar to how people fabricate semiconductor devices that go into our mobile phones and computers. But now these are made of superconducting material instead of semiconductors. And to do that, we have the same kind of equipments, but in a clean room, which is a nanofabrication facility that we have here in Chalmers called MyFab. And over there, we have a very tight control over the environment. We control the number of particles in the air because these are really tiny devices. We don't want these things to fall onto our chips. So these are very well-controlled environments where we fabricate them. And we use tools which are also quite common to semiconducting devices that we have in other devices, but not the material superconductors.
Here at Chalmers, we are fortunate to have a nanofabrication facility, which is actually one of the most important in the Nordic countries. There is both university and industry actors who manufacture the devices here. And this is a result from a 20-year-long investment in this department. Actually, this whole department was originally built around that clean room as a key infrastructure to the research that we do.
So we are part of this Wallenberry Center for Quantum Technology, which has a mission to build a 100-qubit quantum computer. But this is the core project, but in addition, we have the excellence part, in which we also want to push progress in quantum technologies around superconducting circuits to the frontiers. So in this regard, we not only do research with quantum computers, but we also do research with other forms of quantum technologies we realize with superconducting circuits. So one of these is, for example, building a microwave photodetector, a single photon photodetector.
Personally, I think sensing is very interesting. And one thing we found out is that as we try to build a quantum computer, we're building an object that needs to be very isolated from everything else. And as a result, it becomes super sensitive to anything. So actually, based on the same technologies that you use to build a quantum computer, you can build some of the most advanced sensors that we've ever seen.
This is actually relevant, for example, in solving one of the greatest mysteries of the universe, which is why are there so much of matter in the universe which we cannot see? So actually, whatever we see in the whole in our universe, all the galaxies, all the planets and stars, they make up about 15%, 15% of all the matter that we can see, but the rest 85% we cannot see them, and that's one of the greatest mysteries of our times. And one way we think we could solve that is to come up with specialized kind of quantum sensors. So one of them is a photodetector which can detect single photons in the microwave domain. And recently we have come up with a device that can actually do that in the lab. And we're excited about building it up towards those applications.
It would deepen our knowledge about the fundamental particles of physics that ultimately are found everywhere in the universe. I think everything is about people ultimately. The team is very important. We're a team of 15 people now, and we are very diverse when it comes to very different notions of diversity. We have people from all over the world, including Europe, but also other countries. And you ask about the energy. I think it's a luxury to work with these young people that are so passionate about what they do. And most of them, they do it out of curiosity. I do believe scientific curiosity is the start of everything we do here.